Now we are going to talk about the third idea, which is very cute, which says that if you have many communities in your network, so for the sake of simplicity, we'll take two communities and we show that if our cascade starts from one community, then it actually, even if it gets into this entire community, it's difficult for this cascade to get into another community. So we'll be coding and now we'll be looking at this aspect. So for implementing this, we need a graph which consists of two communities, two dense communities. So what will we do? We'll create an artificial graph which will be consisting of two communities. How do we create this artificial graph? We'll create a graph having 20 nodes. So first 10 nodes will be dense, will be connected to each other, and second 10 nodes, means nodes 0 to 9 will be connected to each other, and node 10 to 19 will be connected to each other, and there will be just one link between these two communities. So let's just quickly do it. So I'll just import network X as an X, and I'll also need the random function, so I import random as well. Let me save this as this file as create community graph.py. Okay, so I imported random, and then what I'll do is I create a graph g equals to annex.graph. After this, I create the first community in this graph. So I call the function create first community. And what does this function do is, it just creates a random links between the people. I'll just show you. So define create first community, and we pass the graph here, first community G. And what you do here is, okay, so first of all I add 10 nodes in this community and no edges. So for I in range 0 to 10, what do I do is G dot add node I. So I have added 10 nodes in this graph. Next I want to add some links. So how do I add some links? As we know, these are 10 nodes and there are 10 choose to possible edges between these nodes. So I'll take every edge and I'll put every edge with a probability of 0.5. So I'm doing exactly what happens in an Ados Srini graph, but I'm just coding it manually. So for I in range 0 to 10, so I put first iterator over all of these nodes, and then for j in range 0 to 10, I put a second iterator here, and again to avoid duplication and the same number, if I is less than j, so that I get every pair only once, what do? I want to put an edge here with a probability of 0.5, and I'm quite sure that you know what I'm going to do next, because we have seen it previously. We have coded it also previously. If I want to do some event with a particular probability, I create a random number, random uniform number, real number from 0 to 1. So I get a real number from 0 to 1, r equals to random dot uniform 0 to 1, and then if r is less than 0.5, what I do is g dot add edge from I to j. So I have added every possible edge between these 10 nodes with a probability of 0.5. So this is my first community. Similarly, I create my second community, create second community. And I'm sure that you know that the code is going to be same except for the numbering of nodes. So we can just copy paste this code here, and what I can do is, I know that my nodes are now going to run from 11 to 20, right? So from 11 to 20, and here also 11 to 20, and here also 11 to 20. Everything is done. So 10 nodes I created here. In the similar way 10 nodes I created here, and between these 10 nodes I again put an edge with a probability of 0.5. So what I going to have now in my network, there will be two separate communities, or you can say two components in this graph. So what currently we have made is a disconnected graph. I can also actually show you this graph. So let me show you this graph. Okay, annex.draw g, and then we have a plt dot show, right? And let's run it. Create community graph. Python create. Okay. We forgot to change the name of the function here. So it is create second community. So you can see this graph here, right? We have one community here having which is actually random graph with 10 nodes and 0.5 probability, and one community here. Now we want these are actually components. We can't say these are communities also, but they are components. We want a connected graph. So what I'm going to put next is I'm going to put just one edge between these two communities, so that the communities in my graph are very well defined. I put only one edge. So what I do is g dot add edge, and I add an edge, let's say from node 5 to 15. So let's run it. So you can see here now this is my graph having two communities. We are going to work with this graph for our third idea, for the implementation of the third idea. What I'll do is I'll store this graph, and next dot write GML, and I store this graph as, let me name it as random graph with community. So random graph community dot GML, right? Dot GML. I run it. So you can see a graph here, random graph community.gml. Okay, so now we are ready to so we have a graph with community, and we are ready to see the impact of cascading on such a network. So I'll actually take my code from here and let's save it here. So we'll do all the changes here. Let's call it idea3.py. okay. So first of all, which is the graph we are going to work with is random underscore graph underscore community, one thing. And then let's change the payoffs a little bit, or let's keep it the same. So let the payoffs be 10 and 5, and let my starting nodes be 0 and 1. Okay, and what I'm interested in is to looking at how will this cascade going to occur, and let me look at this in every step. I want to see the graph at every step. So you can see I'll just show you the code. It is the same code which we have written previously. So here we load our graph. Here we set all the nodes to have the action B. Here we choose the initial adapters. We set the initial adapters. We draw the graph. Next, this is just a while loop in which our process runs again and again. Terminating condition, as we have discussed before. Action dictionary, we calculate the next snapshot, and then we plot the next snapshot. Exactly what we want to do. So we just the code is very simple. We just have to run this code and see what happens. So let's implement it. Let's execute it. Python idea3.py. Okay, so this is your initial graph, and the nodes 0 and 1 are infected here. I have adopted the idea, and then you can see that 0 and 1 have adopted back the behavior B, but these other 4 nodes in this community have adopted this behavior A. And then you see more nodes have adopted this behavior A. and this one node in this community have also adopted this behavior A. And then you can see that most of the nodes in this first community where the cascade started have adopted the behavior A. And then you see one community has completely adopted the behavior A, while in other communities still everybody has adopted just the behavior B. And you can keep running it again and again, and you can see that this behavior is not passing on to the other community. It remains stuck to this first community only. So you can see that this cascade, it keeps trapped in the first community itself. So this graph is not going to change. It will just keep running for 100 iterations like this, and your cascade has actually come to an end. So if you remember, during the lecture we discussed that there are 3 stability conditions. First is everybody in this network adopts A. Second is everybody in this network adopts B. And third is some nodes in this network adopt A while others adopt B. So you can see that it is the third condition here. Some nodes in this network have adopted A. Other nodes in this network have adopted B. And then we have looked at what should the network look like for the third condition to happen, and that was the presence of communities. And that's exactly what's happening here. Here are 2 communities. One community has adopted one behavior and the second community has adopted a different behavior.